Hello, welcome. Today we're going to be looking at equation of state. Equation of state. What is equation of state? Equation of state is a mathematical relation between state functions and variables. Any mathematical relation between state functions or variables. Now, what are state functions and variables? State functions and variables are those characteristics of substances that you can use in determining their state. Example, water. Water can be in various forms: liquid, solid, or gas. Those are the states of water. What property of water can you use in telling that this water is in liquid form, or gaseous form, or solid form? You can use temperature. You know that if water is at room temperature, it will be water. If it is in a very low temperature, it will be in form of ice. And if it is above 100, from 100 above, you can call it vapor. So with temperature as a state function or variable, you can determine the state of water. So anything like that, you call it state function or variable. But it's not only temperature, you also have pressure, you also have volume. So any relationship or any mathematical relation that connects one state function to another or to others, we call it equation of state. So these state functions can be temperature, it can be pressure, it can be volume, it can be internal energy. So that's what we're going to be looking at today. So today we're going to be looking at equation of state, and equation of state is a relation between state variables or functions. And these state variables or functions could be what? Temperature, pressure, volume, or internal energy. So you can say this is a relation between pressure being a function of volume or temperature. So this is an example of a state function, and this is actually the ideal gas law, where pressure is related to others. So you can put pressure in this form. It's a function, that is the expression of R, T, and all this. So now, why do we need state functions? What do we use them for? Or why do we need equation of state? We use equation of state in doing calculations that tells us, if you're telling me that this is the volume, what is the pressure? You can easily relate and tell the state functions or variables. So you use it to determine the state function. You use equation of state to calculate. Let's say you're using a piston, as I have here. If you increase the temperature of the substance inside and the volume increases, this piston will move. So how do you know the volume when you increase the temperature? So if I say you give me a temperature of 70 degrees here, Celsius, and the volume is still here, then if you increase it to 100, how do I know the volume? You know that the volume is going to do what? Increase. So this piston is going to be pushed up, because increase in temperature will cause increase in volume or pressure. Actually, you can also talk about pressure. When you increase the temperature, the pressure will increase. So given a temperature, what is the volume? So you can use this relation to find it. So that's why we need equation of state. Now, this is what we call ideal gas law. That is the foremost equation of state that everybody knows about. But you see that this very equation, if you use this relation to solve problems, when you are designing big things like the boilers that are used in industries, there's going to be explosion, because this is not a true representation of the relationship. In ideal gas law, it is always taken that the pressure of the liquid, the pressure of the fluid, is always due to the contact with the surface of the wall or the container. But the force of attraction between the molecules of that fluid is not taken into consideration. And also, the volume, the actual volume of the substance itself, is taken to be very infinitesimal compared to the volume of the whole container. That is the assumptions for ideal gas law. But in true life, those things are not true. There is actually attraction between the molecules of the fluid and the actual volume of the fluid itself. So to take into cognizance these two things that I just mentioned, there are also other equations of state. And a good example of them is what we call van der Waals equation. This is van der Waals equation. You can see that this equation is analogous to this, only that it has this, which is known as force of interaction between the molecules, and it also has this factor telling us that apart from the total volume of the container, there is also a volume of the fluid. So making these two things available in this equation makes this equation to be more of a true representation of what happens in fluid. So this is van der Waals equation, and this is improvement to this. But it is not only van der Waals equation that was done to be an improvement to this, to be used in solving other things. So you can only use this equation if you're solving simple ideal gas based on these two assumptions that I made. The actual pressure is only caused by the fluid particles hitting the wall and not via their interaction. And also that the volume of the fluid particle itself is very small. There is an assumption that if this is the container, the volume of the gas, if you bring them together, it will just be here. You understand? It will be very, very small compared to the whole volume of the container. But now we believe that the volume actually takes a lot of space, and that is this B. And that is why we have this van der Waals equation. But other people did more studies on this equation of state and found out several other equations that are even more correct than the van der Waals equation for solving real gas. For solving what? Real gas. So you find out that when you're doing applications like you're designing a boiler or you're designing all those steam things, all those things has to do with real gases and not ideal gas. So for you not to cause problem of explosion, you need to use such equations and not this one. So these equations of states are classified into three. Some textbooks will give you more classification, but for this lecture, we are going to be considering three classifications. Cubic equation of state. Whenever you see EOS, simply means equation of state. Cubic, and under that we have van der Waals equation, like we've written here. You have Sauvé-Redlich-Kwon equation, and you have Penn-Robinson. In subsequent classes, I'm going to be digesting all this for you. You also have Vira equation that utilizes Z, compressibility factor. You also have what we call empirical equation of state, which has the example as Benedict-Webb-Robin equation. So in subsequent classes, we are going to be looking at all these equations of states and see why they are better than these other two that I've already explained. So like I told you, there are some things that we are not taking into consideration when the ideal gas law was put. So in actual sense, real gases have volume and they have force of attraction. So all these parameters will be more explained, making it to be more correct in these other equations when we look at them. So in subsequent classes, we'll be looking at van der Waals equations, Sauvé-Redlich-Kwon, Penn-Robinson, Benedict-Webb, and other Vira equations and other forms of equations of state. If you like this video, please hit the subscribe button. I'll be supplying the answers to the assignments in the subscription part of this video. I hope you enjoyed it. Thank you, and God bless you.